Hello to everyone, my name is Pietro Barbieri and the title of our work is Enhancing Expressivity of Checked Corecursive Streams. For what concerns the motivations of our work, we wanted to build a calculus for processing streams and represent them with a finite sets of equations. Okay? Why do we care about streams? We can simulate real-world sensor data and also test complex IoT systems. In our calculus, functions are regularly corecursive, which means that we can avoid non-termination thanks to a mechanism of cycle detection. We also go beyond regular stream by having not evaluated operations that allow us to define even non-regular streams. On top of that, we added an operational characterization of well-defined streams. This is a procedure that happens during the evaluation and states whether a stream is well-defined, which means whether a stream is safe to use for the user, okay? One cannot really talk about streams without mentioning lazy evaluation, which is a well-established solution for streams. In particular, Haskell, for instance, we have some examples here. We have the stream 1-2, which is defined in this way, just alternating 1-2. But we also can define a stream like from n, which is the stream of all natural numbers starting from number n. However, in Haskell, we cannot inspect the whole structure, okay, of a stream if we want to check whether these two streams are equal, 1-2 equal 1-2, even if the stream is simple, like in this case, we cannot do that because the Haskell will try to inspect the entire structure, okay, in a never-ending fashion. Moreover, we can also write something like this: bad stream equal bad stream, which is clearly an ill-defined streams because any access to any element of this stream will lead to non-termination. Indeed, it is not possible to decide whether a stream is well-defined, okay, in Haskell. A sort of complementary approach, and maybe a less famous one, is regular corecursion. Here, infinite streams are finitely represented by sets of equations, okay, built upon the stream constructor. In this way, we can encode the regular streams, cyclic streams, okay, and functions are regular corecursive, which means that the execution keeps track of pending function calls, thus avoiding non-termination. In this framework, our function 1-2 is encoded as an equation, in this case a fairly simple one, x equals 1 to x. Okay, with this approach we can inspect the entire structure provided that the stream is regular. Okay, in this case, if the stream is regular, we can compute something like the equality, okay, which gives us the result true. However, as a downside, we cannot model non-regular streams in this framework. For instance, we cannot assign a value to function from n. What we wanted to do in our approach was to keep the benefits of regular corecursion, but also try to go beyond them by having non-regular streams. These are two examples written in our calculus. We have the function repeat, which is a simple repetition of number n. We also have function from n, which similarly to Haskell computes the stream of all natural numbers starting from n. Moreover, in our calculus we have a decidable procedure to check whether a stream is well defined, and in this way we can throw away something like bad stream, something like we do not want to have to deal with because we will incur in non-termination. This is the syntax of the calculus. I'm not going to give you too many details, but I just want to point out that a program is a sequence of mutually recursive function declarations, and then function here for simplicity can only return streams. For what concerns the expressions, we have variables, we have the if then else, we have the constructor of streams, we have the tail, and then we have binary operation. These are interesting operations since they are computed pointwise on a stream, and we have numeric operations, but also the interleaving operator, which computes the interleave of two streams. And lastly, we have the function call. Let's see some preliminary examples to have a hint of what's happening in the semantics here. Okay, this is the definition of our beloved function 1,2. What the semantics does is that it computes a result, and the result is a pair. Okay, a pair with a value and an environment. The environment stores information about the stream. Okay, in this case, everything is fairly simple because we have just an equation with x equals 1 to x. Okay. A similar thing happens for the stream repeat n. If we call repeat 1, we get as a result y in the environment where y is associated with 1 followed by y. Okay. We can also do rather complicated stuff. For instance, the increment of a stream, which computes the increment by 1 of all elements of S. And please note that this S could be either a regular stream like 1, 2, but also a non-regular stream like from. Okay. In this case, we compute the summation on 1, 2 to show the result. And the result is something of shape x plus y, where x is equal to the stream 1, 2, and y is equal to the stream repeat 1. Okay, it is clear that x plus y will give us the result, but we do not compute it. And we only inspect it when we want to access an element. For instance, in this case, we want to access the first element of this thing here. And what the semantics does is that it keeps the result and computes the first element on it. Okay, element 0 on this stuff. Okay, since this is a pointwise operation, we simply distribute the access, and we have to access the first element of x and the first element of y. Then we have to check the environment and unfold these two variables. Thus we have 1 to x at position 0 and 1y at position 0. At this point, everything is straightforward. We just have to compute 1 plus 1, which is 2, which is the correct result. Okay? For what concerns the semantics, we have a fairly simple judgment in a big step semantics. We have on the left-hand side an expression to be evaluated. We have an environment which stores information about the stream. In particular, we have variables associated to streams. Okay. Then we have a call trace which stores calls. C is a call, and in particular, this is done to have this mechanism of cycle detection. In particular, anytime we find a new call, we store it in tau, and by the time we find another call, we check tau, and if the call is present, we can stop the execution, thus avoiding non-termination. The result, as we already seen, is a pair where we have a value and an environment. For what concerns values, we can have open stream values that are streams that are not fully executed, like we have seen for inc before, okay? And also we can have basic stuff like numeric values and Boolean values. This is the semantics. I'm not gonna bore you with the details. I just want to point out that it exists, and it is fairly simple since the rules are just in these two slides. The only thing to note is that at some point in the execution, we have this WD, which is the well-defined check. So by the time we compute a result, this result is checked. And if the result is deemed well-defined, the user is assured that the stream is safe to use. Okay. For what concerns the access to stream elements, we have this rule at, and here in the conclusion we have the standard semantics where we have a stream and a number, which is the index we want to access, and the result is n, but the result is computed with an auxiliary function called at, which operates inside an environment and tries to retrieve the element we need. Okay. Function at is defined in a inductive way. The definition is very simple. These are all the cases, okay, I'm not going to give details, but just to point out straightforward stuff, we have the base case. If we are looking for the first element in a stream where the first element is n, we simply get n, and then all other cases are inductively defined. We try to go on, we try to inspect the stream, okay, and look for what we need. Let's see some more complicated examples. Here, the aim is to just give you an idea of what is possible to do with our calculus. We reported here some examples. For instance, the stream of all natural numbers, which is defined in this way. Then we have powers. We have two streams for powers, nat to pow. At a given element x gives us the result x to the power of n. Okay, then we have its cousin called the pow, which at each element x, at its position x, will give us the result n to the power of x. Okay. Then we have the stream of all factorials. Okay. And lastly, we can, for instance, define the stream of all Fibonacci numbers. As you can see, these definitions are fairly simple, in particular the one of the Fibonacci numbers, which resembles the mathematical one, which were the first two elements and then the recursive definition. Okay. For what concerns functions, we have here some common functions on streams. For instance, function sum computes the stream of partial sums of the first I plus 1 elements of S. Then we have this function sum exponential that uses this sum to compute the stream of all terms of the Taylor series of the exponential function. And please note that by calling this function, we get the entire stream at once. Okay, and when we want to access the element at position I, for instance, we get the correct result. Another important operation is the aggregation. Okay, we can, for instance, aggregate over a window, in this case over a window of size 3, and we can compute, for instance, the sum, okay, over this window. In a similar way, we can also define the average, okay, over a window using this function agg and divided by n. Okay, let's talk a bit about the well-definedness property. And in particular, as already said, a stream is well-defined if it is safe to use. Okay, what does it mean? We have to reason on the environment, because the environment, as we saw, it's the description of the stream. Okay, so our definition of well-definedness is given over an environment. Okay, so an environment is well-defined if with a function at, we can access any element of any streams, any stream in raw. Okay, so we are saying that we want any access to elements to terminate. Okay, let's see some example to see what is going on. We have a few environments. For instance, this one, which it's fairly simple. We can indeed say that this environment is well defined because we just have x, which is a simple stream, 1 to x. We can access any element of the stream in a safe way. Okay, and y is the tail of x. The tail of x is 2, 1, 2, 1, etc. So again, the stream is the environment is well defined because we can access any element to of x and y. Another stream is this one. We have x, which is defined in terms of y, so we have to check y. But y here as this undetermined behavior. We have y equals y. Okay, it's the same as bad stream equal bad stream we saw in the initial part of the talk. Any access to elements of this stream will lead to non-termination. So we deem this environment non-well-defined. Okay. The last example is this one. We have the stream x, which is fine because it's fairly simple. We have just ones, 1, 1, 1, etc. But y is defined as y plus x. So this is an impossible equation because even if x is well defined, we cannot say the same for y because if we try to inspect, for instance, the first element of y, we have to inspect the first element of these two variables, but we will fall into an infinite loop, and thus this environment will be not well defined again. Okay, we developed an algorithm. This is the inference system. Again, I'm not going to bore you with the details, but I just to point out that it exists. It's fairly simple. This stuff in red is the same as we saw in the semantics. Okay, so everything starts from here and we go whenever we need. The basic idea of this algorithm is that we count how many constructors we have and how many tail operators we have, and at some point when a cyclic reference is found, we must ensure that more constructors than tail operators are traversed when we find this reference. Okay, we store this information in a map M. Okay. We developed an optimized version of this well-defined check. In particular, the time complexity of the presented algorithm in the worst case is quadratic. Okay, in the number of steps required to go to the conclusion. Okay. In particular, this is due to the fact that in this map, I'm not going to give details, but in this map we have associations. We store the number of constructor and tail operators for each variable. So anytime we find a new constructor, we have to update it for each variable. Okay, this is a time expensive operation. We developed an optimized version that achieves an n log n time, so in the worst case. However, we decided to keep both versions since this last one is a little bit more complex, and we used the first one for the proofs. And clearly we have a theorem stating that the two versions have the same semantics. Okay. For what concerns the result of this work, we have that the well-definedness check, if it holds, we are guaranteed that the function at always terminates. Okay, this means that the well-definedness of a result prevents non-termination in accessing elements of a stream, and this is an important property because if a stream is deemed well-defined, it means that the user can safely use it inside his or her program. Lastly, we have another result concerning the time complexity of the well-definedness check, which we showed it can be computed in n log n time, which is a fairly decent time. So, coming to conclusions, let's recap what we have seen. We presented a corecursive stream calculus that goes beyond regular values by also allowing the possibility of having non-regular values like our function from n, which we saw before. Then in this calculus, we encoded a well-definedness check that prevents non-termination in accessing the elements of a stream. For what concerns future work, we would like to study the possibility of making functions more flexible. Indeed, there is an enhanced version of regular corecursion called flexible regular corecursion that allows the user to specify the behavior in presence of a calculus. So we would like to study this property. And lastly, we would like to reason on the equality of results, because with the way we encode results, that is by equation, the equality becomes a lot less straightforward. Okay, and that would be all. And thank you for your attention.